Hello everybody. So today we are continuing our discussion of entropy, moving into the second law of thermodynamics. And there's been a lot of build up to this. So today is the day we're actually going to write down what the second law of thermodynamics is. Now I want to remind you of a few places we've been leading into today. We've discussed how we have phase diagrams in which we can plot different properties. So let's say, for example, we have pressure and specific volume. And on the phase diagram, we can plot different points. All right? And these points represent the state of a system. So each one of them have coordinates that are PV coordinates, if this is pressure and volume. We could have pressure 1 here, pressure 2 here, volume 1 here, volume 2 here. Over here we could have P3, V3. I think you get the idea that we can plot points, and at every point we have a representation mathematically of the state of that system. And we've at length addressed the three-dimensional version of this, which is P, V, and T. So plotting the properties at different states. Then we recall that we addressed the fact that we can have paths that go between these. And this was a question on your exams, that the name of these paths were process paths, all right? So there's some process, thermodynamic process, that takes us from one point or one mathematical state to another. And these points can be connected up with these lines representing processes. So something is happening, all right? Now the way that we can change between points, we talked about, and I will draw a dividing line here, because this was another topic that we've discussed, which is the first law of thermodynamics, essentially telling us that there are two ways to transfer energy. One is work, and the other is heat. And these things are not to be understood as energy in and of themselves, but as a name for a process of energy being transferred. And so, given the energy can transfer back and forth, we can change from state to state. And we know that heat and work aren't like the dots on this diagram, but they're like the process paths. Their value, the length of that path, depends on which path is taken, all right? So this is how we can transfer and move around between those points. Now, that moves us into something that we've been addressing that we are going to build on formally this lecture, which is that we have an intuition about which processes can physically happen and which processes can't. And I want to start, I'm going to call on that intuition several times in today's lecture. And here's the first time I'm going to call on that intuition. We have discussed processes like running a current down an electrical wire, and that wire then causing the room to heat up, increase in temperature, so therefore transferring electrical work energy into heat energy. And we discussed how intuitively we realize that work that we've used electrical work to go into heat can't be recreated by heating up the room. We cannot reverse that process. And so I want to define for you what the definition of a reversible process is, all right? And this is a process in the very sense of these process paths, a process changing our state from one thing to another. In this case, we're talking about the temperature of a room increasing. So our little process path is taking us in the temperature direction on our diagrams, all right? Now, but this can be anything, this is general. So a reversible process means that we can go backwards perfectly with no effect on the surroundings. To refresh your memory on what the surroundings are, those are defined as everything on the outside of the system boundary. We have a system, its boundary, and the surroundings outside of it, all right? So, if we have a process that we're able to go forwards and backwards, transfer one way, transfer the other way, and surroundings does not know or care that we're doing that. There's no energy or heat or anything coming in from the outside, then it's reversible. We also have the idea of an irreversible, spell that right, an irreversible process. And as you can expect, this is going to be defined as the opposite. So we cannot do all that, right? We cannot go backwards perfectly with no effect on the surroundings. So reversible and irreversible processes. Now, a few things about these. A reversible process is a supertask. I hope that we've talked about that enough times in labs, and I brought it up in one past lecture, that you have an intuition for what I mean. So, first of all, these reversible processes do not exist in the real world. So that's a big point to think about for a second, that we're gonna talk about this whole concept, but it's not really a thing, all right? So in the real world, we can never go backwards perfectly with no effect on the surroundings. It's impossible. We can get close though, and that's where I hope this concept of supertask comes to mind as a theoretical limit. So think of it like this. We're getting better and better at going backwards perfectly with no effect on the surroundings. And here's our limit, right? This is reversible. It's a hard limit of this is the best we can ever do. We can perfectly go backwards. And we can think of approaching this limit and getting closer and closer and closer and closer and closer, but never actually hitting it. It's exactly like I talked about stacking the blocks. Go back. If you need search supertasks, again, I recommend the Vsauce video explaining this. So it is a limit that is used theoretically, and you'll see problems in your homework set that tell you to assume this process is reversible. What they're doing is say, assume that it's mathematically perfect. And you guys aren't strangers to this. We do this in lab for various things. Assume this, assume that. Just assume it's perfect. But I want you to know that it's never actually, really, totally perfect. Okay? So in real life, all real processes are irreversible to some extent. It's just that some are really irreversible and some are closer to being perfectly reversible. Okay? Now, that brings us to the idea that we are going to start talking about cycles of processes. And in the future, down the road, there's basically a whole study of cycles that we're going to do. Famous cycles and what cycles things run on, like air conditioners and refrigerators and your car and things like that. So this is just touching into the world of cycles for right now. But essentially, a cycle is when we undergo a process and come back to the same place. So right here, in my initial example, I drew a cycle. We've got arrows that go around and return to the same place. And that's the sense in which it's a cycle, is that on a process diagram, we go around and come back to the same place. Now, why do we want to restrict ourselves to talking about cycles? Well, because if we're going to come up with a thermodynamic law, this is the only case that we can even really say anything about with certainty. All the other cases are like weirdos. They're out there. So how can we really study any of the properties when something goes and comes back and we can say this is something about that process. If it doesn't come back to where it started, then how are we supposed to study anything, right? That's just weird, that's just messed up. So what we're gonna be studying here are cyclic processes, which are nice because then we can study them. We can say, are they reversible, are they irreversible, things like that. So recall that we had the first law of thermodynamics, which was that the change of internal energy equals Q minus W, all right? However, if we're on a cycle and we come back to the same place, so now we're going to specify this first law to dealing with cycles, then we're literally starting with all of the same properties as we ended, right? That's what it means to be a cycle. Nothing changes between the very beginning and the very end. Maybe in the middle, but by the time we end, we're right back where we started. That means that by the time we end a cycle, our internal energy is the exact same. So delta U, any change of internal energy, is 0. It can't have changed, all right? So in a cycle, this side of the equation is 0. 0 equals Q minus W. And that allows us to do this, simply add the W over to the other side, and get the relation that W equals Q. Okay? So notice that all we've assumed is a cycle, but this is still fairly general. Okay? Now we have our work and our heat being set equal. All right. So here, where does our intuition come in? Let me raise this board. Here's how we might draw it diagrammatically before we formalize it. We know that from the examples we've talked about, if we have work, like again, that current on that wire, if we have work coming in, that can all be converted into heat. Now remember, work and heat, we're talking about flows, all right? Don't get confused and think I'm talking about tangible, like energy forms. I'm talking about flows, but we can always convert that into heat to then dump energy into our room, okay? So, work flow, we can 100% convert to heat flow. Work to heat, 100%. But heat, we cannot convert always to work. So this is what our intuition tells us, that for going from heat to work, we've got some sort of inefficiency, or we can measure it with the letter eta, again, for efficiency. So here, eta is 1. 100% is transferred, eta equals 1 always. Here, eta could be 0.9, 0.99, 0.25, 0.5 for half. It could be any efficiency you want, anyway from 0 to 1, okay? But it's always going to be slightly less than 1. It's never going to reach perfection. So it's not always 1 here. We have some sort of thermal efficiency. Now, let's try to formalize this intuition that we've got here. And here's how we do that. Imagine actually going about this, converting work to heat, okay? Or converting heat to work. We're interested in studying this case. So imagine a machine here. And this is our heat to work, hope you can read that, heat to work machine, that's what it says. So this machine, at this moment, like I said, later on we're going to study the processes and all the parts and stuff. Right now, it's a black box for us. We don't care what happens inside this machine. There's a cycle going on in here, all right? Some sort of cycle that's trying to get this job done for us, heat to work. We're not concerned with the details. We're just going to look at what comes in and what comes out of this box, right? Before we even get into the cycle, what are we dumping in? And then once we're all done with the cycle, what are we pulling out? That's what we're going to look at. So we know that heat to work machine, we would like some Q in, some heat to flow in, all right? So this heat is going into our machine. We know that out of our machine, we're going to get some work, because that's what we're doing, converting heat to work. Now, where does this intuition come in? Well, we think that given this, which seems to make sense to us, any such machine is going to have to lose a little bit of heat out, right? I've drawn this as a smaller arrow because it's not like it's dumping all of it out. Most of it's going into work, but we're gonna have to lose some. Now, can I prove that? Right now, wait on a second. Right now, I'm actually gonna write that this is an intuition that we have. It makes sense to us to assert this, that we're gonna have to dump a little bit of heat out because all of this heat will not be perfectly converted into work, all right? So going on this premise, using this intuition, we can write down the equation. We know that Q in is gonna be equal to the work plus Q out. That's just writing down an equation to show what I've got there on my machine. And then if we were going to write this efficiency down, you're familiar with how to determine efficiency. So it's going to be the energy out over the energy in. So the energy out is the work, and the energy in is Q in. Okay. This can also be written, just manipulating the algebra here a second. If I move the Q out over, then work can be written as Q in minus Q out, if that makes sense. That's the same over Q in. And this here can be simplified down to 1. So this is not doing anything profound. I'm just rewriting this efficiency in a different way that you may see it sometimes. So it can be written as 1 minus Q out over Q in. This is all pretty straightforward from our study of this heat to work machine. All right? Now, imagine for a second with me, let me divide this off. Imagine for a second that we said, all right, well, if the problem is we can't get all this into work, could we just turn all this into heat out? Could we eliminate the work? So let me draw this again. This is our heat to work machine. And this time we've got a bunch of Q in flowing, and this time we've got all of it coming out. So I've redrawn a similar thing, only this time there's no work. We've said, let's not even try to get work out of it. Let's just take our heat to work machine and basically treat it like a pipe. Q flows in and it flows straight out. It just goes straight through, all right? So Q out is the same amount as Q in. No work. Now, here's a second intuition that we've talked about. Here's an intuition that we have. It makes sense to us from our experience that if heat is flowing this way, it's just flowing through our machine, then it must be flowing from hot to cold, right? So up here, wherever it's flowing from has to have a temperature hot, and wherever it's flowing to has to have a temperature cold, right? I've labeled it TH and TC for hot and cold temperatures. This is another intuition that we have discussed. Okay? The fact that heat can only flow from hot to cold on its own, and it can't flow from cold to hot. Again, can I prove that? Just wait and see. All right? I also want to, okay. So, now, let's try and look at some of the we're going to bring entropy in this for a second. I want to review some of the things that we've talked about that are all equivalent. So I want to make a list up here, okay, that there's going to be, in our process, we think, Oh, this is for a cycle device. This is all for a device, this machine that's running in a cycle, all right? We think that there's gonna be some Q out, a little bit of heat that has to be wasted, because our process is always slightly irreversible. The only true reversible processes are perfect ones. So if we had a perfect process, then that would be reversible, okay? But in the real world, those don't exist. This also told us that eta, our efficiency, had to be either less than or equal to 1. It's equal to 1 in the case of our reversible process, which really can't quite happen. But in all real world scenarios, it's less than. So the main point here is that it certainly can never be over 1, and it's only equal to 1 for this theoretical thing. And then also, another way of writing this Q out is that our change of heat for the whole system, well, if we're always going to lose some, we're always going to lose a little bit of heat, then looking at our change of heat, this is always going to be less than or equal to 0. It's going to be negative. This makes sense. If we're always going to lose a little bit, then our total heat change will always be a negative number. I'll write that. That this is going to be a negative number. The equal sign is only in the perfect case, right? You'll get used to understanding this. If this is actually equal to 0, everything's perfect, but for the real world, it's never going to be exactly equal, always at least a little bit negative. Now, having reviewed that, we want to bring in the concept of entropy. All right, we've talked about entropy. We know that entropy, as understood by physicists, is this conversion factor, but understood by modern physics and information theory in the modern era, it's also this measure of randomness. So how do those two things go together? Well, remember that up here, where it's hot, we've got really energetic and really random particles. If you need a refresher on this, I think that we did a good job explaining this back in our discussion of temperature and what it is. And I discussed in detail how temperature is really a measure of how different these paths of the particles were from each other. And measuring in sort of a way, temperature is measuring how random are these particles all flying around, all right? And it also has to do with how much energy are in these particles. Whereas down here, where it's cold, these particles are just barely wiggling a little bit, and they're also more organized. So up here, in our hot temperature, we have disorganized or disordered, all right, disorder. And down here in our cold temperature, we have order. So now we can try to bring in entropy. We know that as we lose heat, right, and I'm going to write it like this. I'll write it up. Well, I'll go down here, okay? dq, the amount of heat flow, first of all, is going to be proportional to that temperature. So there's some number here that's times the temperature. When we talked about this on Zoom, this is how we make sense of that definition I gave from physics of entropy, of what it was. It's a conversion factor between energy, this is energy here, okay, and temperature. This is our entropy. So as we change in energy, change of heat here, then here we have a change of entropy, okay? We have a delta S, and we've introduced S already, what it is for entropy. Now, why would this be the case? That this conversion factor tells us something about order and disorder. Well, think about it. These particles here are highly disordered, and as the heat flows into the more ordered state, this thing is gaining disorder, right? The thing that it's losing, the Q out, is order. That's going toward the order. So our system, our machine, is losing that. But the thing that it's pulling in, our Q in, sucking into that machine to work, that is disorder. So over time, it's losing the ordered energy and sucking in more disordered energy. That's just a nature of going from hot to cold. And so the order or randomness of this is slowly increasing. That's why this conversion factor right here is delta S, or our change of entropy. Now, notice that delta Q is defined to be something that this is losing. So this is actually a negative quantity, whereas delta S, we know that it's gaining. So there's an overall negative sign on this, okay? Negative delta Q is equal to delta S times T. And this is where, okay, so let me write what this tells us then. We have negative delta Q divided by T equals delta S. And I will circle this equation, okay? And notice that this is where we get our units, the fact that entropy for physicists has units. This is energy in joules, and this is temperature in Kelvin. So we have that the units of entropy equals the joules per Kelvin. Okay, that's just a little side note, but that's where we get this. Again, if you look at it in this context, it comes from being that conversion factor. The fact that temperature and energy are closely related, and the way to convert between them is this idea of entropy. Okay? Now, the last thing that we want to look at on this board is a pretty simple thing, but we have to think of it. Notice that delta Q is always a negative number, right? Less than or equal to 0. Delta S is minus delta Q. So this part is always going to be a positive number. And T right here, well, that's a temperature in absolute scale. Don't get confused about that. Maybe I should have mentioned that earlier. We're talking absolute temperatures. They only go down to 0. This is going to be a positive number. So if this thing is true, that delta Q is less than or equal to 0, then we have another true statement we can make, that delta S is greater than or equal to 0. All right? Hopefully that makes sense. Let's write down the second law of thermodynamics. What I'm going to do is I'm going to make you realize that those intuitions that we've had are the second law of thermodynamics. We just have to write them out. So the first intuition we had right here was our intuition was we needed to lose a little bit of heat. We could not perfectly just go Q in and just to work out. There's always a little bit of heat loss in that system. Well, I've got this written out. Second law of thermodynamics. For a cycle device converting heat to work, there must be some energy lost in heat. That's exactly what our intuition was, and that's the second law. Now, this version of the second law was coined by two physicists. Their names were Kelvin and Planck. And so this one, because we're going to find that there are multiple ways of saying the second law of thermodynamics, but this one is called the Kelvin-Planck statement of the second law of thermodynamics. Come back to this at the very end. Let's go look at our other intuition. It was right here. Our intuition that we had said that if we were just going to have a machine that didn't have work associated with it, and all it did was a big pipe to suck heat from one side to the other, then it had to go from hot to cold. It couldn't on its own go from cold to hot. That is another way of saying the second law of thermodynamics. Check this out. For a cycle device, energy flow via heat. Energy cannot flow, via heat from a low temperature to a higher temperature without work input. Right? It's got to go, if there's no work input, it's got to go higher to lower. It cannot go lower to higher. Another intuition we had that turns out to be another way of writing the second law of thermodynamics. And this was by a physicist named Clausius, and so it's called the Clausius statement. You can tell by the fact that I haven't raised the board all the way, we've got one more. And notice that in this discussion, we came up with this fact. Stand here. Delta S, or the change of entropy, must be greater than 0. It's equal if it's perfect, and that can never actually happen. So it's delta S is greater than 0. That means that entropy is increasing. And we have our modern statement of the second law of thermodynamics. For a cycle device, entropy increases. It's so simple, and that's why we like it today for a modern definition. This is the definition that really led into the information theory side of things agreeing with us. This is a much more foundational and fundamental definition. Look how these two almost seem messy compared to that. It's so simple. And but notice that in order to understand this definition, we have to understand entropy. These two definitions were actually made before entropy was properly invented. So they don't involve entropy in their definition, whereas that one does. And I don't know, the other thing to note is that it's just different in the sense that it's so much cleaner and more foundational. However, in upcoming lectures, we're going to address the fact that all three of these, as well as many other statements, I could continue this list of ways of saying what the second law of thermodynamics is, and they're all equivalent. All of these mean the same thing. They're not telling me different truths about the universe. They're just three different ways, among others, of writing down the same underlying truth about the universe. And that is the second law of thermodynamics. All right, looking forward to continuing, but I'll leave it off for here for right now. Thanks, guys.